Hey everyone. As we continue our transition to statistical inference, I wanted to record a video that you're able to pause, rewind, and rewatch through some of this content. As always, please ask questions. I'm available in lots of different modalities. So this content is difficult, this transition is tough, but you can all do it. Let's get started. This is a discussion on foundational inference tools. We're going to focus on categorical data here rather than numeric data because categorical data is a little bit easier to work with. I'm going to break this discussion up into a few pieces to make it a little bit more manageable. But here we go. So um, I'm going to skip the warm-up problem in the slide deck. If you were in class this week, we did it. And so let's move forward. So highlights for this series of discussions, I think there will be at least 2, if not 3 videos here. We'll talk about descriptive statistics versus inferential statistics as sort of a launch pad. We'll talk about the 2 major types of inferential task, estimating a population parameter or testing a claim about that population parameter. We'll have a reminder on the sampling distribution and the central limit theorem, which is the one that allows us to use the normal distribution or eventually distributions that are at least like the normal distribution to model probabilities associated with drawing samples with specific characteristics. We'll look at sampling error. And I think we'll probably pause there to end the first part of this video, and then we'll move on to confidence intervals for parameter estimation. That's how we're going to answer or address this first task, estimating the value of a population parameter. Then we'll do an example, probably pause again, and look at hypothesis testing for claims about population parameters. And again, that's how we'll address the second type of inferential task here. I have a bunch of example problems at the end of this slide deck. The videos will go through one problem each, but I encourage you to return to the slide deck and practice with those additional examples. And there's a summary at the end of the slide deck, so we probably won't address the extra example problems or the summary directly in the series of videos, but you know where to access them. So to launch off descriptive statistics and inferential statistics, descriptive statistics is where we have been. This gives us the tools necessary to describe the data that we have. I collected a sample of 25 individuals. I asked them a bunch of questions, collected data on them. Descriptive statistics allowed us to assess or to describe those 25 individuals. Nothing more, nothing less. We use summary statistics for that. Sample mean, sample median, sample standard deviation, frequencies, proportions. We also looked at data visualizations, which allowed us to tell a little bit more of a story with the data that was part of our sample, where summary statistics generally gave us a 1-number summary. And before we talk about descriptive statistics, it's important to clarify the difference between sample statistics and population parameters. We've done this a couple of times now, but let's do it once more. A sample statistic is a summary measure that belongs to a sample. It only belongs to that 25 individuals that I collected data from, or the approximately 7,500 different properties that we had data from earlier this semester in and around Austin, Texas. Those summary measures could be a sample mean, which we often denote by like X bar or the variable name with a bar over it. The sample standard deviation, which we denote by S, or the sample proportion denoted by P. And so we can calculate sample statistics directly on the sample data that we have. We just apply a mathematical formula to the sample data. A population parameter is different. It's a summary measure that belongs to an entire population. We have different letters to denote these, and in fact, we transition to a different alphabet altogether. It's common in statistics when you're referring to population level values to use Greek letters for those. So we could have a population mean denoted by the Greek letter mu, a population standard deviation denoted by the Greek letter sigma, and so on. What's important is that the sample statistics correspond to those population values, but they won't be exact replications of them. So what I mean by that is the sample mean, x bar, provides you with an estimate for the population mean, mu. The sample standard deviation, s, provides you with an estimate or an approximation for the population standard deviation, sigma. And similarly, a sample proportion will provide you with an estimate for a population proportion. And we'll see that in action throughout this discussion today. The big challenge here, and the entire reason we need inferential statistics, is because it's not generally possible to find these population parameters directly. We can't observe them because we can't really conduct a census. It's not feasible to do so. And so samples are our only lens into populations. And so inferential statistics then consists of tools and methods for using sample data as evidence to make or test claims about a population. So we're going to have to reason through the sample data that we observe to try to either estimate the value of a population parameter or to test a claim about it. What that means is that there's going to be uncertainty associated with everything that we do here for the remainder of our time together. So the tools and procedures for inferential statistics. Seriously, we're often much more interested in describing entire populations than we are in simply describing our sample data. Population level questions are just much more interesting. We can't typically calculate population parameters directly unless we were able to somehow conduct a true census, but generally that's not possible. We've got a couple of tools and procedures that can help us use sample data to make or test these claims. However, taking a sample involves randomness. And so when we take a sample and calculate a sample statistic, that's a random process. We don't know exactly what's going to happen before the sample's been taken. And in fact, if we repeat this procedure exactly over and over and over again, different samples are going to result in different sample statistics. And for that reason, because of the randomness, the tools that we're going to use here depend on probability. One of the tools that we're going to use is called a confidence interval. This will capture a population parameter with some degree of certainty. We cannot have 100% certainty and still provide a meaningful or useful interval. Generally, people will try to capture population parameters with 90% confidence or 95% confidence or higher, or even sometimes lower percentages of confidence. But we'll have to set some meaningful, reasonable level of confidence before we construct an interval. These, again, will be used to estimate the value of a population parameter. So if you're wondering, hey, what is this population parameter? A confidence interval is what you're going to use in order to find it. Hypothesis tests are going to be able to test claims involving a population parameter. So maybe we're wondering if a population parameter has changed over the past few years or since some major incident. Or maybe we're wondering if two subpopulations have different values of a population parameter. Hypothesis tests will give us the framework for investigating those questions. So again, we're going to have sort of a foundational setup video here to start. I'll hit the pause button, record a separate video on confidence intervals where we motivate them and work through an example. And finally, we'll have a third video, I think, on hypothesis tests. These are complex procedures that are going to take some time to get used to and to gain comfort with. You will be able to do these things. Slowly but surely, you will gain comfort and you'll get better at them. We'll practice together. So before we jump into any of those specialized tools, some reminders on proportions and some motivation here. Proportions are used to summarize categorical data. Categorical data results from questions whose response results in a grouping. So, have you attended a college sporting event at SNHU? Possible answers there are yes or no. We'll have a yes group and a no group. Are you a vegetarian, a vegan, a pescatarian, or an omnivore? Again, your response there sorts you into a group. In the cases above, if we're interested in proportions, at least at this point during our inference journey, we're going to measure the size of one group. This results in a binary classification, which we saw earlier this semester when we were working with the binomial distribution. In the cases above, we can, the first question is already a binary sorting question. We might be interested in the proportion of SNU students who have attended at least one sporting event in the university. How big is that group? Is it 60%? Is it 85%? Is it something less? In the second scenario, we don't currently have a binary classification happening. We have 4 categories, but we can transition this into a binary classification problem by declaring a subgroup or a combination of subgroups that we're interested in. So maybe we're interested in the proportion of the adult population in the United States who choose not to eat any meat or any fish. These are people who identify as vegans or vegetarians. We can combine those two groups together and estimate the proportion of the population that falls under those classifications. Proportions measure the part out of a whole. They're typically represented as a decimal value between 0 and 1. That's actually going to be the best, most useful format for us in our work with conducting statistical inference on proportions. Alternatively, you can use fractions or you can use percentages. We'll honestly see both. To compute a sample proportion, you do so by taking the number of observations with the characteristic that you're interested in, the number of people who are either vegan or vegetarian, and divide it by the total sample size. And a sample proportion, as we mentioned earlier, serves as an estimate for a population proportion, even though it might not be exactly the population proportion. Let's talk about sampling variation. So sampling variation is what we got at earlier when we described taking a sample and calculating a summary statistic or a sample statistic as a random process. From one sample to the next, there will be variability and uncertainty. So when we collect sample data, we get an estimate for the population parameter. And we do this because we want to know the population parameter even though we can't measure it directly. We cannot reliably conduct a census. So I'm going to take a random sample of 17 individuals from a hypothetical voting population that's considering a fictitious proposition B52. That proposition would make it illegal to pop bubble wrap in public places. And the results of these 17 individual voting plans appears below. And so if I'm interested in the proportion in favor, I can count them up. I have 1, 2, 3, 4, 5, 6, 7, 8. 8 individuals out of my 17 who are in favor. I can calculate that sample proportion by taking 8 and dividing it by 17. And I'll get about 47.1%, or 0.471 is the proportion. And the question now becomes, is the population proportion in favor of proposition B52 equal to 0.471? And I'm willing to bet that most of us would say, well, probably not. Because this proportion belongs to only those 17 people who we talked to by chance, by way of our random sample. And if we took a new random sample of 17 individuals, we may get different voting preferences. But at the very least, that sample provides an estimate for the population proportion. the population proportion is probably somewhere around 0.471. But what do we mean by around 0.471? We'll need to do a little bit more work to get there. So here's another random sample of 17 individuals' voting preferences on Proposition B52. I have now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 in favor of the proposition. 13 out of 17 gives me a new estimate of around 76.5%. This is quite a bit different than the proportion we estimated earlier. But again, it's an estimate of the population proportion. So maybe the population proportion now we estimate is somewhere around 76.5%. But again, it's unclear what we mean by around. These results were really different. So what can the results of a random sample actually tell us? Let's look at some pictures. So here in the plot on the right, you can see that black dot represents the original sample statistic, the original sample proportion that we got from that first set of 17 individuals. It was just below 50%. Here's our next sample. It was just above 75%. And if we went out and talked to a third set of 17 people, here's a hypothetical proportion that we might get back. You'll notice these proportions are bouncing around. Let's round this out by talking to 97 more collections of 17 individuals. So getting 100 samples. And here are the results. And so we might at this point be willing to identify that, well, okay, maybe that first sample wasn't such a great representation of the population as a whole. We'll find out that unfortunately we still have to deal with that. But looking at the collection of 100 samples, we might identify that, well, the proportion in favor looks like it might be around 75%. Because if I averaged all of these sample proportions together, that's about where I'd end up. But each sample has pretty wildly different proportions. We're extending all the way from below 50% up to 100%. There's lots of uncertainty in the sample data here. So that sample of 17 individuals is really pretty small. That's what led to having so much uncertainty. We can reduce the amount of uncertainty we have by increasing the number of individuals in our samples. So let's take samples of 113 individuals instead. There's nothing special here about 17 individuals or 113 individuals. I chose them randomly. Here are 100 random samples of 113 voters each. And you notice the level of uncertainty is not so wide anymore. It's still relatively wide, extending maybe from around 60 or 65% up to about 80%. But we're no longer having such uncertainty that it is possible that below 50% are in favor or even 100% are in favor. The results, though, are similar. If we averaged all of these proportions together, we might land around 75%. And so the population proportion in favor might be about 75%. And so in summary, here's what we've done. We've identified that each sample provides us with a summary statistic, here a sample proportion. That sample proportion serves as an estimate for the population proportion. Each sample results in a different summary statistic, though, and that is referred to as sampling variation. Change in the summary statistic from one sample to the next. Let's talk about sampling variation and sample error. We'll revisit those 100 samples of 113 individuals. Here they are. I've added a blue dashed line through the mass of these dots at the true population proportion. I've been hiding this in the background. It's how I generated the data. And that blue vertical line, hard to see as it is slightly below 75%. It's at 74. And what we can do is, if we know that the true proportion is 74%, we can calculate the sampling errors, how far off each sample statistic was from the true population proportion that it was seeking to measure. Some of those sampling errors are wide, they're large. Some of those sampling errors are really small, they're very close to the true population proportion. Some of those sampling errors are positive. We overshot the population proportion, while some of them are on the other side. We undershot the population proportion. But on the whole, that distribution of sampling errors is approximately normal. Well, you might not be convinced that this is approximately normal. This is our distribution of 100 sampling errors. So let me show you 50,000 of them. So here are 50,000 random samples of 113 individuals each, and the sampling errors associated with those random samples. You'll notice this is quite bell-shaped. We have a peak in the middle, and as we move out further and further to either direction, those larger sampling errors become less and less likely. So here, nearly all of the sampling errors are within 10 percentage points of either side. All right, so let's summarize sampling variation and sampling error. Again, each sample provides us with a summary statistic. That's a sample proportion here that serves as an estimate for the population proportion. Each sample, though, results in a different summary statistic, and that's what's referred to as sampling variation. Each sample's summary statistic has some deviation from the population proportion that it's trying to estimate, and that deviation is called sampling error. The distribution of sampling errors is approximately normal. We saw in that most recent purple histogram of 50,000 sampling errors. I've put an asterisk here because the normality of that those errors depends on the success-failure condition being satisfied. Our sample sizes have to be large enough that we should expect at least 10 successful outcomes and at least 10 failure outcomes. Another way to phrase that is that our samples should be large enough that at least 10 outcomes should be yes and at least 10 outcomes should be no. And because of the fact that these sampling errors are approximately normal, the distribution of the sample proportions is approximately normal as well. And according to the central limit theorem, that normal distribution is predictable. So what I've done from this darker purple distribution to the next click, which results in a lighter distribution, is I'm drawing on top of this distribution of simulated sample proportions the normal distribution that is described according to the central limit theorem. And you'll notice that those distributions are quite close to one another, especially out in these tails. The central limit theorem here for proportions suggests that the sampling distribution of sample proportions is approximately normal. That's what that n is standing for. And the mean of that normal distribution is at the population proportion. So the population proportion here is the center of this sampling distribution, 74%. And the standard error for that normal distribution. Remember, when we switch to the sampling distribution, we use standard error instead of standard deviation to describe spread, and this is simply to avoid confusion with terminology. But the spread of that sampling distribution is also predictable. It's the population proportion times 1 minus that population proportion divided by the sample size, and then take the square root of that number. These two things together allow you to construct the normal distribution that approximates the sampling distribution. This is nice because now we can use the tools that we've developed over the past few weeks together in working with the normal distribution, like p-norm and q-norm, to calculate probabilities or to calculate boundary values associated with samples resulting from this distribution. And so, when is the distribution of sample proportions approximately normal? Again, we've just discussed it, but the central limit theorem requires that sample sizes are large enough. And we had the success-failure condition to tell us that. This is the one, again, that we discussed on the previous slide, indicating that our sample size is large enough that we expect at least 10 successes, and we expect at least 10 failures. If P is the probability of success, remember that the number of trials times the probability of success gives you the expected number of successes. And similarly, the number of trials times the probability of failure gives you the expected number of failures. However, there's a serious problem with the analysis that we've gone through and the analyses that we've been going through. In all of these recent discussions, we've been simulating a sampling distribution to help us. But doing that requires knowledge of the population parameter ahead of time. And if we knew the population parameter, then there'd be no need for statistical inference. And so we don't know that population parameter, and we can't simulate this sampling distribution. The big problem is that we don't take 100 samples or 50,000 samples. We take a single sample and we attempt to draw inferences from that one sample. But the problem is, which sample do we get? Do we get this one, where the sample proportion is bigger than the true population proportion? Or do we get that one, where the sample proportion is much smaller than the true population proportion? Or do we get this one, where the sample proportion is really close to the population proportion? We have no control over it, and we need some way to estimate the uncertainty associated with those different samples. Now, the first two samples that I'm showing you here are kind of extreme. They're almost the furthest above the true population proportion, or almost the furthest below the true population proportion. Those samples are very unlikely. If you look at a vertical strip above this solid black dot, there are almost no points out here. And even nearby, there are very few. Similar for this one, there are almost no points in a vertical strip near this data point. However, if we look at the third data point, there are lots of samples whose population proportions landed at about this sample proportion. And so in some sense, this last sample is more likely than either of the first two that I showed you. And we can leverage those ideas when estimating our uncertainty. All right, so I think I want to stop here for now. And in the next video, we'll pick up where we left off. I'll kind of recap what's happened so far, and we'll talk about confidence intervals. Thanks, everybody. I'll see you in the next video.